On New Zealand's North Island, the Waipoua River drains into the sea. Upriver, things are not so pretty. More than a century of deforestation for farming has created some of the most dramatic erosion in the world. Here, raw gullies and collapsing hillsides dump tons of mud into headwaters, choking wildlife and vineyards downstream.
People in New Zealand have been trying very hard to find a way to restabilize the hill slopes and try and mitigate some of these problems with sediment that they're having. And so, yeah, that's where I come in.
For land managers attempting to restore the Waipoua Basin, or eroding landscapes anywhere, finding the source of sediment moving downstream is critical. But where exactly is the sediment coming from? Reeser and Professor Paul Bierman have developed a new rapid method for pinpointing this pollution and tracking it downstream. They measure a rare form of the element beryllium that forms high in the atmosphere. This isotope, beryllium-10, falls to the earth and accumulates, sticking to sand and sediment. For Bierman and Reeser, the amount of beryllium in their samples works like a secret map for navigating eroding landscapes. Their results were published in the journal Geology, and their work happens in one of the most specialized geology labs in the world.
This is the Cosmogenic Nuclide Extraction Lab, and in this lab we remove small amounts of very rare isotopes from aliquots of quartz and other minerals. And the purpose of that is to date landforms on Earth's surface and to determine how quickly parts of Earth's surface are eroding. So two things are new in this paper. One thing is the analytic method that we used. We measured the beryllium-10 that's adhered to the outside of grains, and we measured it in river sediments. And that's only been done a couple times before, and it's never been done with a mission to figure out where that sediment was coming from. The second piece that we've done is worked down a river network. So Luke started by collecting samples in the far, steep headwaters and worked his way down the main channel of the river till it emptied into the ocean. And so what he's determined there is that there's a very predictable change in the number of beryllium-10 atoms adhered to the sediment as you move downstream. And what that change represents is the input of sediment from a huge gully or landside complex that basically has no beryllium-10. And then as the sediment's carried downstream, the inputs from side channels and tributaries of material that has increasing amounts of beryllium-10s.
This is actually an example of one of the samples from a river channel in the Waipoua Basin that was collected and brought it back here and pulverized it and then eventually measured the meteoric beryllium-10 that's adhered to each one of these little sediment grains.
We start with sediment, and for the work that we did in the Waipoua Basin in New Zealand, we take that sediment back, we sieve it to a specific grain size, that kind of sand you would typically find on a beach, and then we crush it to a fine powder. And after that, we extract the beryllium-10 by fluxing the powder, very little of it, half a gram, in the presence of some very strong chemicals that break down the bonds that hold the minerals together. And then we take that fluxed material, we essentially have melted the rock, we put it in very pure water, and only the beryllium and the potassium are soluble at that point. And that lets us extract the beryllium. We can remove the potassium with some other chemical treatments, and then we have basically pure beryllium. We take that material out to Livermore Lab in California, where we measure the ratio of beryllium-9 atoms to beryllium-10 atoms. And because we know we've added a certain number of beryllium-9 atoms, once we have that ratio and we know how much beryllium-9 we've added, it's a simple multiplication to get how much beryllium-10 was in our sample.
So now we can come in a very accurate manner, sort of characterize what portions of the drainage basin are problematic and which ones aren't so problematic for land managers to target.